Okay, thank you. So this is joint work with Noé de Santo and Clément Pit-Claudel. And around a year and a half ago, we started a project to formally verify some linear time regex engine for JavaScript regexes. And so just like any formal verification project, we would need three things, right? We need algorithms to verify, we need some kind of specification to verify it against, and then a proof of correctness that would relate the two. And ideally, we would have all of these three things in a proof assistant like Coq. Now, the algorithms, we do have them now, but it's not the topic of today. We presented some linear time matching algorithms for JavaScript regexes this year at PLDI. But the topic of today is only about the specification. And so we need a mechanized specification for JavaScript regexes, and you might think that, I mean, it should be quite easy to do. In fact, many textbooks already define semantics for regexes in general, and even Coq textbooks also tell you how to define that. And we've even seen in the past, in previous work, that this kind of model with nice inference rules can be extended to support the features of JavaScript regexes that I will present in a moment. However, this is not the kind of specification we want, because there already exists an official specification of JavaScript, the ECMAScript standard, and this is a reference document that specifies how to execute the entirety of the JavaScript language. And so, of course, it contains a chapter, a 33 pages chapter of pseudocode to tell you how to execute JavaScript regexes. And if we look at those two, the backtracking algorithm of the ECMAScript standard and those inference rules on the right, we quickly realize that those two things are widely different. And it's to a point that it's hard to convince oneself that your system of inference rules is actually implementing the official specification. And with a closer look, we found that in previous work, there were some subtle cases where the specification was just not correct with regards to the ECMAScript standard. And so today, I want to talk about our mechanized specification in Coq, which is done in such a way that it's really easy to audit and to convince oneself that this actually corresponds to the ECMAScript standard. And so we really want to prioritize auditability and faithfulness. So let's take a closer look at JavaScript regexes. Like in many modern programming languages, JavaScript includes regex and supports them natively. And so you can write those kinds of things into your programs, and you don't need any external libraries or anything to execute them. And apparently, a lot of people do. Now, when I say regexes, I don't just mean your standard regular expressions. Of course, we still have all of these nice constructs like concatenation, disjunction, and iteration, but we also have so much more. For instance, we now have capture groups. So when you match a regex with a capture group, you not only want to know if there is a match, but you also want to know for each sub-expression inside parentheses, which part of the string was matched by each sub-expression. And so in that case, I'm trying to match A star B on the string AAB. And I want it to return two things. I want to know that the whole regex matched AAB, and I want to know that the star in between parentheses matched only AA. And this raises a lot of issues, because what happens when sometimes there are two different ways to match a regex? Well, let's just take this other example. I'm trying to match A or AB on the string AB. I could take the first branch, or I could take the second one. And so, of course, the semantics specifies which branch you should take, and in JavaScript, it's the first branch, which means that, for instance, disjunction is surprisingly not commutative anymore in JavaScript. And then you have so many much more complex features. For instance, you can go backwards in the string. So this is a regex that looks for a sequence of numbers preceded by the string ICFP. And so whenever in my matching algorithm I am between the P and the 2, I will go back into my string to try and match ICFP. So this is just a few examples, but we have so many more features in JavaScript regexes. We have lookaheads, back references. We have so many kinds of quantifiers. We have different kinds of character classes. We have negative lookarounds, and so on and so on. And to make things worse, we also have different modes of matching with different flags, flags for case insensitivity, Unicode mode, and so on. And so you get the picture. It's come to a point where it's hard to build a JavaScript regex engine that actually conforms to the specification. And in fact, a few years ago, Firefox just gave up and now uses the JavaScript regex engine that is used in Chrome and Node.js. And also, previously, we found some bugs in Chrome's linear time engine. And so we really want to stick to the standard for all of these complex features. Now, speaking of the ECMAScript specification, as I've said, it's a big pseudocode chapter describing the semantics of the regex, and it does so in a few stages. First, it tells you how to parse a regex, and then how to check that a regex is well-formed. And finally, and this is the biggest part, it tells you in pseudocode how to generate a pseudocode function that corresponds to your regex, and then when executed, will execute a backtracking algorithm that will tell you the result of your regex matching. So here is an example of what it looks like. So we have many pages of functions that look like this. You have a small description and then some pseudocode instruction. So this is a function that will compile a disjunction, for instance. So we want something in Coq that clearly, without any doubt, closely corresponds to this. And so our solution was to define a faithful shallow embedding in Coq of all of these pseudocode functions. So we take one function from the specification, this one, for instance. So once again, some description and then some pseudocode instruction. And then we turn each and every line into Coq comments. And next, we just fill in the blanks with equivalent Coq lines that actually implement the pseudocode. And if you repeat this process thousands of times, you get a full mechanization of the regex chapter of ECMAScript. Now, how do we get to this point? How do we get to that shallow embedding? I would like to highlight just a few mechanization challenges that we encountered along the way. Now, to begin, there are a few pseudocode instructions in ECMAScript that could potentially fail. We have a few assertions, like asserting that I is going to be smaller than j, and we have sometimes accessing an array at some index that could be out of bound. Now, the expectation for these instructions for the committees that wrote ECMAScript is that this should not fail. We don't have any try-catch mechanism. We expect all of these assertions to hold. Now, of course, in our mechanization, we would like to encode all of them as well. And so you could think maybe about using dependent types to try and encode all of these nice invariants into our mechanization. But in our experiments, this has not been great for auditability. And so we use a simple encoding with the error monad, where it scales well to the entire chapter. And if the specification was badly written and an assertion would fail, our mechanization is also going to fail. It's easy to audit, and in fact, we can define some simple notations that clearly corresponds to the pseudocode instructions. Another issue that we had was with non-structural recursions. There are just a few places in the specification where some functions are recursive but non-structurally. Here you see a simplified version of the function that compiles the cleany star, for instance. And you see a recursive call to repeat matcher. But in the specific case where min is equal to 0, you don't have any structurally decreasing argument. And so once again, we could try and explicitly define a measure and give it to a program fixed point, but once again, quite invasive for auditability. And so we simply used a fuel argument that we add to all of these functions that strictly decreases, and so Coq accepts this definition. Now, of course, the first time we want to call this function, we need to compute some minimal amount of fuel that we want to give to that function so that it does not run out of fuel. And we were able to do that, and I'll go back to the correctness of this in a few slides. Now, finally, one last challenge that we had during the mechanization is that a few functions in this chapter were using some kind of what we called non-local operations. So let's look at an example. In this function, there is only one argument, which is a node of the regex AST. And what the function is actually doing is that it's counting the number of capture groups that happened in the original regex pattern before the current node. And so, of course, if you only have the node of the AST, it's not enough to do that. And so to implement it in Coq, we need a bit more. We need to remember the original regex pattern and the position of the node within it. And so we could implement this with a simple data structure that we can just build as we go through the regex with a zipper context that encodes exactly the original regex pattern and the current position of the current node. And so with just a combination of pretty standard and simple techniques, we get to something that is quite auditable and that scales well to the entirety of the chapter. And now that we have a complete mechanization of that chapter, we can actually try and execute it. And so this is what we do. Once we have our Coq mechanization, we can extract it to OCaml and then use melange to generate some equivalent JavaScript code. Note that in various places, this chapter relies on external definitions from the Unicode standard. And so as a result, our entire mechanization is parameterized by some Unicode functions that we need to instantiate in order to have a fully executable engine. And when we do that, we can also check that our mechanization behaves as expected. And so, for instance, we run the official JavaScript conformance test suite, test 262. And of course, this tests the entire JavaScript language, and so it contains also regex tests, around 500 of them. And we could check that our mechanization correctly passes all of them except 3 that timeouts. It happens that the specification in some places uses some very inefficient algorithms, and because we stick closely to that specification, sometimes we are also very inefficient. And now that we have this Coq mechanization that we can also execute, it's also time to do some proofs about them. And so, of course, we can try and prove properties about the ECMAScript specification itself. Now that we encoded all of these assertions and all of these array accesses, we can finally prove that none of these are going to fail. And so we could state and prove the following theorem, saying that for any regex and string, the matchers that are produced by compilation cannot fail, meaning that no assertion can fail and no array access is going to be out of bounds. We can also check, similarly, because we introduced fuel, that we're never going to run out of fuel, meaning that the initial fuel that we computed is always enough. We can check that for any regex and string, the matchers cannot run out of fuel. Next, we also wanted to check that we could use this mechanization to prove some optimizations or some things about regex semantics. And so we formally verified one optimization that is actually currently executed by the V8 engine used by Chrome and Node.js. And this looks like a simple optimization simply when regex R is strictly nullable. And what I mean by this is that whenever it matches something, it can only ever match the empty string. If you have such a regex, then R star should be replaced by epsilon. And on standard regular expressions, this is quite easy, but in JavaScript, of course, we have a notion of priority, we have JavaScript-specific semantics for the star, we could have groups inside that regex and so on, but we were still able to prove the correctness of that optimization. So we could prove that if you compile R star or if you compile epsilon, you get some matcher functions that are completely equivalent. So this has been Warbler, our Coq mechanization of JavaScript regexes, closely following the ECMAScript standard. And so we have really prioritized auditability and faithfulness. We are really close to the original official document. Of course, we can execute it, and we have been able to prove properties about JavaScript regexes. Now, one of the things we wanted to do is that a student, Martin, just finished, is that we wanted to check that there is clear bijection between the comments in our Coq code and all of the pseudocode instruction in the ECMAScript standard. And so Martin wrote a tool that checks that, in fact, all of our comments are indeed pseudocode instructions and vice versa. Also, recently, there has been a new extension of the JavaScript, the ECMAScript specification, introducing yet another flag for JavaScript regexes. And so we'd like to extend our mechanization to support it, but because we've used such a faithful style and auditable style, it should be fairly straightforward to extend our mechanization even without a lot of Coq knowledge. Finally, of course, we might want to still use some sort of inference rule systems to reason about regexes. I mean, this provides a nice induction principle that we like to reason about them. And now we finally have a ground truth so that we can write those inference rule systems and prove it equivalent in Coq to our mechanization. And now we know that we can finally trust those inference rule systems if we do it this way. And of course, in the long run, we want to use this mechanization to be able to formally verify some actual regex engines for JavaScript. Thank you.
Questions?
Thanks for the talk. Cole from UCSD. My question is, now that you've gone through all that lengthy specification, was the pseudocode, generally speaking, something that, like you, in your example, you showed that you can just sort of like have one line of pseudocode, one line of Coq. Was it generally that simple to implement? Was it pretty straightforward, or were there points where like you had to do a lot of guessing or like inspection into sort of like the language that as was written?
It's a good question. So mostly I would say that we don't have to do much guessing. I showed one example where we had to, figure out that we needed some context, and I think that's the most extreme example. So really, the committee that wrote the specification has to be commended for that. It's pretty, unambiguous most of the time.
Thanks.
Thanks.
Hi, Gabriel Radan. There has been some work in the past few years about, transforming all the specification, in particular the DOM semantics and all that, to a slightly mechanized version. So Alan Schmidt, Philippa Gardner, and all that. How does it interact? Like your work and what they did on the semantic of JavaScript and all that. Can you bring both together? How does?
So are you speaking about specifically for JavaScript or
specifically for JavaScript?
Okay. So for JavaScript, indeed, there are a few either mechanization of the JavaScript language, either in Coq or in other kind of languages like ES Meta and so on.
Yeah,
in our experience, none of them targeted the regex chapter. And maybe part of it was this chapter is strangely written in a quite different style than the rest of the semantics. And so it makes sense that all of these sometimes automatic approaches did not work out of the box for the regex chapter, and we needed that regex chapter, so we did it this way. Yes, I think their approach could also be extended for the regex chapter, but at the moment they were not supporting it.
Okay.
Let's thank Aurèle again.